Dr. Friedberg come back? Hmm? Oh, we're almost done actually with Lagrangian procedure. So we'll start Hamiltonian today. We're lagging behind, but interestingly, we're catching up as well. You can ask if you have any question. If you have any question, you can ask. One more minute, we will start. Okay, can you start? Hello?
Yeah.
Okay. Hey, Carl, did you miss something? I cannot hear you, like your microphone is muted. Your microphone is muted.
Yeah, I am muted, but that's because there's a little bit of music playing in the background. I didn't want to disturb people.
Oh, okay. So did
I
you
did
miss
have an outage, but I'm fine now.
Okay. Okay, great. Okay, so this was one part. So for each of the coordinate transformation, we can always find a conserved quantity, associated conserved quantity. Basically, that's initial data of that, it could be momentum or it could be the value of coordinate as well. So what about time translation? So we know our Lagrange's equation is delta L over delta Qi equals to ddt of delta L over delta Qi dot. So
Yes.
let's start having this Qi dot delta L over delta Qi dot. Take ddt of this whole thing. So if you take ddt of the whole thing, you get Qi double dot delta L over delta Qi dot, and then you have plus Qi dot ddt of delta L by delta Qi dot, right? Like this, by product rule.
Yes.
So you can write it as
Right there, that will be there.
ddt of Qi dot multiplied by delta L over delta Qi dot plus Qi dot, and if you use Lagrange's equation over here, what do you get?
Then I will get dl by dqi.
Delta L over delta Qi, right? Also, this Q dot, Qi dot, you can write it as ddt of Qi, like that.
Yeah.
So, so what we can do, we can add two things. So add delta L by delta T and then subtract delta L by delta T. You can do that as well, right? Can you recognize this whole thing? This part?
Yeah, it is basically dl by dt.
This is basically dl by dt,
DL.
right? So it can be written as dl by dt minus delta L by delta T. And on the other side, we already have ddt of Qi dot delta L over delta Qi dot. Like that. Right?
Yeah.
Okay. So I can take this dl over dt on the other side. So I can write ddt of delta L by delta Qi dot, basically this term I have written, minus L equals to negative delta L over delta T, right?
Yeah.
So point is, if my Lagrangian is not an explicit function of time, so in our Lagrangian, like the argument is like Qi dot and T, right? So if that explicit T doesn't appear, then delta L over delta T is 0, right?
Yes.
Yeah.
So if Lagrangian is not an explicit function of time, then there exists another conserved quantity that is we write it as E equals to delta L by delta Qi dot minus L. So this is basically the energy of the system.
Yes.
So
Yes.
this is how we get energy. So it also gives us another important point. So now we need to talk about something about phase space and configuration space. So when we do, like in classical mechanics, there are three concepts. One is configuration space, then state space, and phase space. Configuration space is a collection of position of the particle only. So this is basically a generalized position vector creates the configuration space. Like in 3 dimension, to describe a particle, we just need a position of that particle. So like that.
The R of T.
Yes, R of T.
Yes.
Okay. So in other words, configuration space is basically the coordinates only. So the constituent is like Q1 of T, Q2 of T, and so on up to Qn of T. Basically, generally we write configuration space as Qi of T. That creates the configuration space. Like the only thing that matters is the coordinate. The state space, that's a little bit interesting because state space is constructed out of not only the position but associated velocities as well.
Yes.
So it is constructed out of Qi T, Qi dot of T, and like so on. Like I do not have to write so on. Like for each of the i's, like I equals to 1 up to n, like that.
Yeah.
It's position and velocity, and phase space
Position, momentum.
is the position and momentum, Qi of T and Pi of T. So what's the importance here? So point is to specify the motion of a particle, you need to provide initial data, right? You need to provide things initially. So if you provide initial position only, like initial configuration space, it doesn't define anything.
Yeah.
Still you could have infinite degree of freedom because your initial velocity or initial momentum is not defined. So 2 ways we can do that. We can provide the initial velocity data or initial, like I should write, we could provide like velocity data at 0 or momentum data as 0 as well. So in like here we are already giving like Qi 0, so those are here as well. But
Well, normally phase space and state space should be same because
no.
Pi is equal to.
Is that so? No. For a polar coordinate,
Okay. Yeah.
But this is basically V phi. So those are not same.
Oh, yeah. Thank you.
Okay. So in Lagrangian mechanics, for our Lagrangian, the function Lagrangian, it depends on the state space variable like Qi dot, and so on. Right? Qi and Qi dot, and most possibly T. Problem is, actually there is a difficulty when, actually not difficulty, it's actually one advantage that we couldn't use in Lagrangian. So in Lagrangian, there could be a case like delta L over delta Q J, for example, it could be 0. Like you have a big Lagrangian inside of which one of the coordinate doesn't appear, say.
Yes.
That means for that coordinate, delta L over delta Qj appears. But it means automatically that delta L over delta qj dot is conserved,
Yes.
but qj dot itself is not conserved, right?
Yeah.
But in Lagrangian, the explicitly thing that appears is qj dot, not delta L by delta qj dot. Let's call it something. Delta L by delta qj dot is defined to be the momentum. We call it like pj. So pj doesn't appear in L, but qj dot, it appears in L. So even if you have delta L by delta qj equals to 0, you cannot set your qj equals to 0, because this is not true, but this thing is true. So if we had, instead of Lagrangian, if we had some other variable as like this that describes the system, that considers pj's as the fundamental variable instead of qj dots, then it will be useful, because we could then directly substitute that constant quantity inside of that pj, and our like that specific quantity would be reduced a little bit.
Yes.
So far, do you have any question here?
I'm not clear with this last thing.
So, okay, let me give you an example. Let me give you an example. So let's say you have a polar coordinate system. So in polar coordinate system, just trust me for now that kinetic energy of the system is half m r dot square plus r square phi dot squared. This is the kinetic energy of the system. Say this is the Lagrangian of mine, like a free particle that's moving in two-dimensional polar coordinate, like moving in two-dimensional space, but we have set up a polar coordinate. That's the case.
Okay.
So now we know there must be two conserved quantities, because we had like mx dot to be constant, also my dot to be constant. So here, if we use Lagrange's equation, we can see that delta L over delta R dot, this thing is constant, that's for sure. Oh, sorry.
Here mx dot is not constant.
No, I did not. No, two things are constant. Mx dot is a constant, y dot is also a constant. Because for Lagrangian, it will be like
Yes, dl d phi is equal to 0.
So here, delta L over delta phi equals to 0, which implies
Angular
ddt of delta L by delta phi dot to be 0, right? Which means delta L by delta phi dot is a constant quantity.
Yes, angular momentum.
Yes, angular momentum, but it doesn't mean that phi dot is constant.
Yeah.
This is true. So if like phi dot were constant, like for the let me give you an for the case of R as well. No, okay. So if phi dot were constant, then here we have phi dot, we could substitute that phi dot instead of constant, right?
Yeah, if phi dot is constant, then r is constant, then it is circular motion.
No, if phi dot were constant, say delta L by delta phi is 0, so here delta L over delta phi dot is constant. We know for sure, but what if phi dot were constant? In that case, we could substitute that phi dot here as well. So that would be the coordinate, right? Then we will have just only one coordinate, that r. But as we cannot substitute phi dot to be a constant, we still have to deal with this phi coordinate, because even if it has a conserved quantity. So, but for P5 we have P5 equals to what? Delta L by delta phi dot, which is constant quantity. So that is m r square phi dot. This thing is a constant quantity. Let's see L, right?
Yes.
Yeah.
So we actually can substitute and reduce the Lagrangian to be like half m r dot square plus what? Just do the algebra and substitute it over there. I believe it will be like half m r dot square plus 1 over twice m p phi square over r square, like that.
Yes.
So here p phi is a constant quantity, so I can replace with L. So if I can do that, then see, this L is only a function of r and r dot. We do not have to worry about phi dot at all, right?
Yeah.
But problem is we were able to like solve for phi dot here and substitute back here. But what if this solving was complicated? We cannot like substitute phi dot here. What happens? Then we have to deal with both coordinates. Even one of those has conserved quantity. Like both of them have conserved quantity, but one of those is actually independent of coordinate. So it would be better if we instead of had a function, like instead of L, we could have some another like say M, that is considered as like the phase space function that generates the motion, like L, but that is a function of coordinates. But instead of moment velocities, it has moment as inside of it. Then whenever I see that M doesn't have Q, I could replace P with that. P as a constant thing as well. I do not need to solve this kind of thing. So P phi is L, and I can substitute that directly because it's P appears explicitly over there. I think it's better to give an example. Actually doing the thing and giving the example would be better, but this is the idea.
Okay.
Okay, so do that. Basic point is we are actually trying to change our variable from qi dot to pj, qpi. Like instead of variable as independent variable, we are as a dependent variable, we are considering the corresponding moment as dependent variable. So that's the goal. So to do that, to change the variable of a system, we always use legendary transformation. So if you have a function, so f of x, y equals to f of x, so the derivative of y is like y prime equals to f prime of x. So we can actually, out of this y equals to f of x, we can find the equivalent representation of this curve, but in terms of slopes only, slopes and intercept. So instead of writing this, we could write like this: c equals to c of m, where m is y prime. The equivalent representation of same function.
Yeah.
So how? Using legendary transformation. So we are now, instead of let's do the thing. So let's say you have a function f of x, and at point x comma y, you have a slope m equals to dy by dx. And you actually create a tangent line over there. That tangent line intersects at C0 point, sorry, 0C point. Yeah, 0C point. Then equation of this straight line would be, because it's passing through xy point and also 0C point, also it has a slope m. So m equals to y minus c divided by x minus 0, right?
Yes.
So instead of m, we can write actually, or write like that, doesn't matter. So we can actually solve for c and write c equals to y minus mx, right?
Yes.
Now this is an intermediate state, and it actually mixes two kind of thing, like it has y and x as well, or also it has m and c as well. So one more thing is we actually need to invert the thing. So m actually can be like if you take derivative of y, like you're given with y square, so then dy by dx could be written as a function of x, right?
Yes.
So we can actually write this thing as
Y
some
to the x square.
yeah, oops. Yeah, that's what I mean actually. Yeah. So m actually a function of x we can write as, right? So we can invert this relation, and we can also write
Well,
x.
this is actually true for explicit functions. Actually, for implicit function, it can be very tough to convert, I think.
Yes, the conversion could be difficult. Yeah, that's a problem. But
And also might be impossible, I think.
no.
Sometimes.
In principle, it can be done. So the restriction only is that dy by dx cannot be 0. So if it is identically 0, then we cannot do anything. Otherwise, in principle, you can.
It is either decreasing or increasing. Is the
Yes. So if we can write like that.
So basically, we are collecting y-intercepts for different slopes, actually.
Yes, we are collecting y-intercepts for different slope values. Yeah. So y already as a function of x. So x, and now x we are trying to write in terms of m. Oops. So I can write y as a function of x as a function of m minus m x as a function of m. So now this hand side only of some big function of m. So I have converted my equation into like c equals to some function of m, like that. Let's do an example, then you'll understand. Do this one. So let's say you are given with a function.
Actually,
y
if we see that m is actually dy by dx, and it is a function of x, you have written that, then there should be a unique inverse function. Otherwise, we cannot write x is equal to x of m.
Yes, it has to be invertible. That's the point. It has to be invertible. In general, it cannot be done. In general, like for absolute any case, it cannot be done. But when that dy by dx is not equals to 0, or more, for more general case, the Jacobian is not 0, then you can do that.
Yeah.
Okay, so let's give you an example. So let's say you have y equals to x squared. So the corresponding derivative y prime, which is m, would be twice x, right? So now in this case, x can be written as half m.
yes.
So starting with this equation, c minus y, c equals to y minus mx. You can write y equals to x square minus mx. Then x equals to half m, so half m whole square minus m into half m, so equals to 1/4 m squared, right?
Negative 1/4.
Negative, yeah. So c equals to negative 1/4 m squared. So these two equations, like y equals to x squared and c equals to negative 1/4 m squared, they are equivalent. They express the same thing. One in terms of points, like what is the value of the function when you input x, that's one way. Another way is what is the value of intercept when your slope is m. So in the first case, like y equals to x squared, all we are plotting is different points like this we are plotting, right?
Yeah.
And for the second case, actually, what we are doing, for each of the slope, we are taking the intercept. So for m equals to 0, we have a straight line. Like when m equals to 0, c is also 0. So here, when m equals to 1, say, I mean this amount, so it has to intercept in negative 1/4. That means it should go like this. So it should cut like that or that. When it is it has a bigger value, it should like it has a bigger value, like then the slope should, like, intercept should be more negative, so it should go here if it has a bigger value. So it goes like this, also like that. So these slopes basically creates an envelope for that function. So intuitively you could think like this: if you are given with a function that like that, you're actually considering this so as many as possible, so like infinitely many slopes you're drawing, so that that slope lines, they actually creates the envelope for the function, so they preserve the same information. That's all I'm talking about.
Yes.
Okay, any questions so far about legendary transformation? This transformation is known as legendary transformation. So can you do this? If I give you like y equals to log of x, can you transform it?
Yeah.
Yes, it's not that hard as well. So let's do this as well. So m would be 1 over x, right? Taking derivative. So x would be 1 over m. So c equals to y, which is log of x, and x means 1 over m,
1 over m.
minus x multiplied by x means 1 over m multiplied by 1 over m, right?
Yeah.
M multiplied by 1 over m. So this gives 1. So we are left with negative log of m.
Minus 1.
Yeah. So this is the legendary transformation for y equals to log of x.
Yeah.
This inversion may be difficult, or may not be available in terms of closed form functions, but in principle it can be done. Okay.
Yeah.
Okay. So that's what we are trying to do. For Lagrangian, we have q dot and most possibly t. Or I should write I actually. So qi dot and t. So instead of having qi dot, we are trying to change variable to pi, which are already defined as delta L by delta qi dot. So we
Yes.
can write equals to intercept minus L divided by qi dot minus 0, right?
Yes.
The similar way we did previously for single variable case. So C minus L equals to sum over I pi qi dot. Okay.
Yes. Hamiltonian, basically.
Actually, I made a mistake actually. Here I should write L minus C instead of C minus L, right? It was previously Y minus C divided by X minus 0, right? Not C minus 1.
Yeah.
Yeah, so I made a mistake. So it should be L minus C. So C equals to L minus sum over I pi qi dot. So this new function C would not be a function of qi dots. Instead, it will be a function of pi, right?
Yes.
Okay, so we define our H to be negative of C. This is how we define our H. So it doesn't matter if you define your plus or minus, but there is a reason why we define it to be minus. Well, it will be clear in a moment. So H would be equals to sum over I pi qi dot minus L, which is basically sum over I. Pi means delta L by delta qi dot, then qi dot minus L, right? So this was the conserved quantity we found previously, right?
Yeah.
And that's for time independent system. That's basically the energy. Yeah, so to make it proportional to energy, we considered it to be negative. So if we consider like C, it would be like negative of energy. So that's not a problem as well. We could do that as well, and that's not a problem, and everything will work out same. But to give H a meaning as energy, we did this. So from now on, our H is defined as like as I did in the last line, sum over I pi qi dot minus L. So then one thing has to hold, that is H must not be a function of coordinates like velocities, right? It should be equals to 0.
Yeah.
So let's prove that. Take derivative with respect to qi. So if you take delta this thing, it gives you here you have pi minus delta L by delta qi dot, right? But we know by definition pi is delta L by delta qi dot, so it is 0. So our new function H is not a function of qi dot anymore. It's a function of pi and q. So L was a function of qi dot and most possibly t, and from that we have constructed H such that H is a function of coordinate momentous instead of velocities and time. So now in any moment we find like delta H over delta qi to be 0, we automatically set the corresponding momenta to be constant and reduce down one of the coordinates entirely. So that's the advantage here, and that's a big advantage when we're trying to integrate something. Any questions so far?
No.
No, great. So now let's find the equation of motion in terms of this h, right? That's what we need to do. So we have to start with the definition of our action that was given by s equals to integration t1 up to t2 L as a function of qi dot and t dt. Now substitute that h instead of L. So if you substitute that, so what is the definition of h? Definition of h equals to sum over I pi qi dot minus L. That means L would be sum over I pi qi dot minus h, where h is a function of p, q, and t. So we can write that t1 up to t2 sum over I pi qi dot minus h, which is a function of qi, pi, and t integrated over dt. This is our s, written in terms of momentous, like Hamiltonian. So Hamilton's principle says the equation of motion, equation of motion in the mechanical system is found by setting variation of s to be 0. So take variation of s and see what happens. Okay. So if you take variation of s, now remember you can now take variation of qi as well, pi as well. So you have to be careful. So sum over I pi variation of qi dot plus sum over I qi dot variation of pi, because pi is also a function of time, so you need to write down the variation of it, plus sum over I delta h over delta qi variation qi
minus.
Oh yeah, minus, yeah, I missed it, sorry. Minus, then minus sum over I delta h by delta pi variation pi, and then finally integrated over dt, right? Remember, we are still imposing the boundary condition that variation of qi at t1 equals to 0 and variation of qi at t2 equals to 0. Like endpoint variations are 0, as we did previously. Like variation of qi means basically alpha eta I, the alpha eta basically, which are 0 at the boundary point, right?
Yeah.
Boundary point. Okay, so now collect the variation of pi and collect the variation of qi and qi dot. So if you collect the variation of pi, you get t1 up to t2 sum over I qi dot minus delta h by delta pi variation pi. This is one part, right?
Yes.
Plus sum over I
think we can take the sum out of the integral.
yeah, we can do that. Yeah, definitely. Like do the sum later, and we can do that as well. Yeah.
We can also use Einstein summation convention.
Yeah, we can do that as well. Okay, so we are almost done, so don't worry. Okay, so sum over I, Pi variation of Qi dot, then minus delta H by delta Qi variation Qi dot, Qi, and then dt, right? Do you guys agree?
Yeah.
Okay, great. Now, see, these two things actually, it has, both of them have Qi variation, but one has like Qi dot. So what we did, we integrate this thing by parts. If we integrate this thing by parts, so what we need to do is integrate that part, like Qi part first. So we are left with Pi, sum over I, Pi, delta Qi, evaluated at T1 up to T2, minus, now take derivative of the other one. So integration sum over I, Pi dot variation Qi, right? So if we integrate this thing by parts, we get these two terms.
Yes.
So what is this term?
It will be 0.
It will be zeros because variation of Qi, configuration, variation on configuration space at the boundaries, that always vanishes.
Yeah.
Right? So this thing is 0. So all we need to replace this thing by this thing.
Yeah.
So we can write T1 up to T2 sum over I Qi dot minus delta H by delta Pi variation Pi plus sum over I. So now we have a minus sign. So minus Pi dot minus delta H over delta Qi variation Qi dt. This is what we get. Variation of S. Okay.
Yes.
So setting this thing to be 0. So variation of Pi, that's an arbitrary variation. We can vary our momentum as we want. We can vary our coordinate as we want, right? So those things has to, like those coefficient of those has to be 0 independently. So we get Qi dot equals to delta H by delta Pi, and also Pi dot equals to negative delta H by delta Qi. So these are our Hamilton's equation of motion.
Yeah.
So what's the difference between Lagrangian and Hamiltonian here then? Lagrangian was one second order differential equation, but for Hamiltonian we have two first order differential equations. Okay.
Yes.
So let's compare. For our Newton's law, we had our F equal ma. So for each of the particles, we had this. For Lagrangian, each of the coordinates we had delta L over delta Qi equals to ddt of delta L over delta Qi dot. And for Hamiltonian, we have definition of momentum to be this, and rate of change of momentum to be this. So basically, if you want to compare with Newton's law, so this part is actually F, like dp by dt equals to F. dp by dt, oh sorry, not that one, other one, this one basically. This one gives dp by dt equals to f, if you want to compare with Newton's law, and this part gives the definition of momentum, like for Cartesian coordinate our momentum was like this. So in Newton's law, in Lagrangian mechanics, we did not need to define the momentum explicitly. Without defining the momentum, we were fine. But now we are defining the momentum and using it as another equation.
Yeah.
Okay. So I think we are at the position to take a break. After the break, we'll come back and do some problem with this Hamiltonian mechanics and compare the advantage and disadvantages. Let's take a break of 10 minutes. It's 12:01 p.m. here. 12:11 at 12:11 p.m. we'll come back.
Bhai, I have a question.
Yes, sure.
Well, the variation we have used at D'Alembert's principle and the variation we used at the time of variational calculus, are they the same thing?
Yes, yes.
Okay, so okay, our eta of x is sorry, alpha times eta of x is that variation
Yes.
that we have also used at D'Alembert's principle.
Did we?
I have to repeat the sentence again.
Did we use variation of Q? Oh yeah, we did. We did. Yeah, we did.
Okay.
Yes, alpha times eta of x is variation of Q.
Yeah. So what is the meaning if we take the time derivative of that quantity, time derivative of the variation?
Yeah, that's
Is-
basically alpha times eta dot.
Yeah, is there any physical meaning of this thing, or we can do it something like, for example, a particle is moving, moving in a path which is not the
So
actual.
we never consider like variation of variation of Q dot explicitly. Always when you encounter that kind of thing, you integrate by parts and you eventually end up having like variation of Q itself that you understand explicitly and you can deal with.
Okay.
Hello. I have skipped the hello. Can I ask a question?
I think Diva is not here.
Okay, all right.
Hi, you're here again.
I'm back.
Ah, it's okay.
Why
So
someone had a question?
yeah, sure.
Okay.
Who had a
I
question?
have a question. I have a question.
Yeah, sure.
At the last section, we have Hamiltonian was negative. I may have skipped why we took the negative sign.